Hello everybody, my name is Logan Marshall and I'm an undergraduate mathematics student here at UTA. I'm currently in my final semester of undergraduate studies, and as a part of that, I've been participating in some computational neuroscience research under the guidance of Dr. Pedro Maya. In particular, I've been focusing on the topic of attention, and what I present today will be a culmination of some of my research efforts over the past couple of months. So without further ado, let's get to the poster. Okay, so here's my research poster. It's titled Sustaining Attention, iMetrics as Cognitive Predictors. Essentially what I'm trying to do in this research is classify individuals as either attentive or inattentive based only on what their eyes are doing. I attempt to do this by using eye tracker and pupillometry data collected in a recent experiment which measured subjects' reaction times in a psychomotor vigilance task. I'll talk a bit more about this task in a moment, but first, why is this important? Just about everything that we do relies on our ability to pay attention, and so any information that we can gather on the topic is valuable, whether we gather it through our own experience or through scientific research such as this. Furthermore, if we're able to efficiently determine whether or not people are attentive on the fly, we may be able to improve our ability to do things such as identifying inattentive drivers or determining how attentive students are during an online course. I'll leave it to you to imagine how this information may be useful. Alright, so this psychomotor vigilance task, what's this about? I'm using data obtained from a study conducted by Dr. Matthew Robinson, who is an assistant professor here at the psychology department of UTA. He had 396 subjects participate in this task for a consecutive sequence of 140 trials each. Each trial has 4 phases, and they're depicted here in Figure 1. For the sake of time, I'm not going to go into all of the details of these different phases. Just note that subjects' reaction times are being recorded while their eyes are being tracked. And if you would like to take a closer look at the diagram, feel free to pause. So now we know the diameter of subjects' pupils throughout each trial, as well as where they were looking at on the screen. But does this information really tell us anything? I've plotted a sample subject's pupil diameter throughout a trial here. These red dotted lines denote the beginning of a phase, and this black dotted line shows when the subject reacted. As you can see, there tends to be a significant effect on the subject's pupil diameter when the phase of the trial changes. This seems to imply that we may be able to get some useful information out of this eye data. So here's the fun part. Now I'm going to try to classify individuals as attentive or inattentive using this data. The first step to doing this is determining for myself what an attentive trial looks like. Or rather, how quick of a reaction time will I require for them to be considered as attentive? For this research particularly, I decided to use a threshold of 350 milliseconds. Although, as I mentioned in the discussion section of this poster, this should be experimented with farther. The next important thing to note is that I'm only going to be considering eye data from the last 2 seconds of this zeros phase of the experiment. So basically, I'm trying to predict how far this black line is from this red line, how great the reaction time is, based on what's going on here. To do this, I extract 8 simple features from the eye data: the mean and standard deviation of each pupil's diameter, and the mean and standard deviation for the deviation of each eye's gaze from the center of the screen. This left me with a set of features and an associated class for each trial, allowing me to begin training several different machine learning classifiers. I tried quite a few different approaches, but as you'll see in the results section of my paper, the best models were a multi-layer perceptron, a type of neural network, and a k-nearest neighbor classifier. Using the multi-layer perceptron, I was able to classify individuals as attentive, meaning they had a reaction time of less than 200 milliseconds, or inattentive, meaning it was greater than that, with a balanced accuracy of 63%. After achieving these results, I decided to experiment a little farther, and I added these subjects' unique identification numbers for each trial. When this was included in the vector of features, the k-nearest neighbor model performed the best, obtaining a balanced accuracy of 70%. Admittedly, neither of these accuracies are particularly impressive, but they do seem to indicate that there is useful information encoded in the eyes. I believe that if we continue to experiment with this, we will be able to improve our accuracies farther and perhaps even accomplish some of the goals that I laid out in my problem statement. There's a lot more I would have liked to talk about in this presentation, but being that we're short on time, I suppose this will have to do. Thank you very much for your attention, and have a great day.